So we've seen the special case of extensive form games, the games of perfect information. It's a good time now to move to the general case of games of imperfect information. Let's start by asking the following question. When we take a game of perfect information, can we transform it to the normal form game? And the answer is, in a very straightforward way, yes. We simply take all the pure strategies in the extensive form game, make them into pure strategies in normal form, and we're done. The mixture now in the normal form is exactly the mixture we get in games of extensive form games. Let's look at our familiar Battle of the Sexes game. As we know, player one has two pure strategies, player two has four pure strategies. Let's simply write them down in matrix form. And here we have for player one simply the selection of this movie, Pride and Prejudice, or the second movie, Lord of the Rings. Whereas player two has Pride and Prejudice in its two decision nodes, Pride and Prejudice in the first one, Lord of the Rings in the other, and similarly the other two strategies. Now we simply, in a very straightforward way, took the extensive form and turned it to normal form. The question is, first of all, so which is better? Why have two forms if we can always make this transformation? Well, you can argue the following. You could argue that the extensive form gives us more information, gives us more timing information about what happened before what. On the other hand, you could argue that it sometimes makes spurious distinctions. Let me give you an example. Imagine even a single player perspective. In one case, the player can take three actions, A, B, and C. In the other case, it can take one of two actions, A or D, and then immediately that same player take the actions B or C. These are superficially very different game trees, in fact, single-player game trees, although intuitively they really capture the same situation where we simply delayed one decision and took it later. So those are arguments for and against the extensive form. Some would say that the normal form is unambiguous. It doesn't let you guess about what's being represented. On the other hand, it can be much, much larger. Even in our example of the Battle of the Sexes, we had 7 nodes in the tree as opposed to the 8 cells in the game. That's a very small difference, but in general, the difference can be exponentially large. On the other hand, and similarly, one could argue that the normal form game loses information because different game trees translate to the same normal form. Turns out to be an interesting philosophical debate that is not settled, and we will simply note that the two forms exist and move on. But whereas we could translate from the extensive form to the normal form easily, how can we do the opposite? How can we take the non-sequential Battle of the Sexes, for example, and turn it into an extensive form game? We capture it with information sets. Whereas before, player 2 has 2 nodes and knew in which node it was when it was time to act, here it cannot distinguish the 2 nodes. In other words, player 1 may be going in this direction or in this direction. Player 2 knows that it is its turn to act, and it knows that it can either go left or go right, but it doesn't know whether it's doing it in this node or in this node. And this is our way of capturing it, very intuitive. How do we make this precise? Well, we have the exact same formalism of games of perfect information, but add information sets. How do we add information sets? Well, we have, first of all, we use the notation x sub a to denote all the nodes in which it's a's turn to act. And we now take a partition of all those nodes. What is a partition? Well, a partition is taking all the nodes and dividing it into sets, here denoted I1, I2, and so on, such that every two sets are disjoint, and the union of all of them consists of all the nodes. So that's a partition. And we also make the requirement that if we have two nodes in a given information set, it better be the case that the actions available in these two nodes are identical. And all of this captures the intuition that the agent can't tell apart these nodes in the information set. Because even if I didn't get to observe what you did before it was my turn to move, if I see that I have different actions available in the nodes, I can tell them apart. So that's the notion of partition, and we add that to the definition of an extensive form game. We get games of imperfect information. And the strategies are for the most part unchanged. Pure strategies simply turn from being what to do in each node to what to do in each information set. You don't know which node you're in, you know which information set you're in. So that's what a pure strategy is. Mixed strategies are simply a mixture of pure strategies. And similarly, behavioral strategies we can't mix in each node because we don't know which node we're in. So instead we mix in each information set. And a simple observation is that games of perfect information are really a special case in which all the nodes are simply singletons. That is, sets consisting of exactly one node. The final thing to note about games of imperfect information is a subtlety having to do with behavioral strategies and the distinction from mixed strategies. We already saw that in games of perfect information, the two capture the same set of games. It is still true in games of imperfect information where agents have what's called perfect recall. I won't define it formally, but intuitively, a game is a game of perfect recall if at every information set, each agent remembers exactly the path that took the agent there. That is, the set of information sets and what was done until it got to where it is right now. In such games, again, the expressive power of behavioral strategies and mixed strategies is identical. But in games of imperfect recall, that is no longer the case. And let me give a brief example of that. Here is a game, a two-player game, where player one moves first. And then, depending on what it did, if it went here, it gets to move again at the game's end. And if it goes here, player two gets to move again, and then the game ends. Now, the subtlety is that the player cannot tell apart these two nodes. We sometimes capture information sets with an oval encompassing both and sometimes with a dotted line between them. So these two nodes of player one lie in the same information set. So the way to think about the agent makes a move here, then doesn't remember whether he did or didn't take the move, and needs to choose again in which direction to go, and then the game ends. So now let's think about the strategies in this game. Pure strategies are very clear. Agent 2, of course, has two strategies, left and right, and so does Agent 1. It has one information set with left and right options in it. So those are pure strategies of left and right. And when you mix among them, you can mix in whichever way you want. So, for example, suppose you mixed equally. There's a probability of 1/2 of going left and probably 1/2 of going right in the information set. What distribution did that induce on the leaf nodes? Well, let's see. If you chose left with probably one half, then you would definitely go down this path and end up here. So you, with probability 1/2, you'd end up here. And if you chose right, well, you would end up here, and then the actual distribution that among these two depends on the distribution on the strategy of player 2. Let's say, for the sake of discussion, that player 2 is randomizing 1/2 as well. So you get a quarter here and a quarter here. Notice that the probability here is 0. So there is absolutely no way, no matter what mixture, what weight you give each of the pure strategy in a mixed strategy, the game will never end in this outcome. Because if you chose left, you chose once and for all left. If you chose right, then you chose once and for all right. And it's just a question of what's the probability that you do either of those things. Whereas if you had a behavioral strategy, that the story is different. Suppose you had a behavioral strategy that told you that you randomized half-half in this information set right here. So what, and let's assume as before that player 2 randomized half-half. So what probability distribution did that induce on the nodes? Well, with probability 1/2, you'd be going down this route in the beginning. And with independent probability 1/2, you'd be going here and here. And so that means you have a probability of 1/4 of ending up here and 1/4 of ending up here. You have probability of 1/2 of coming down this route, and again the 1/4 and 1/4 here. And so we see that in this case, behavioral strategies let us get at this hidden treasure that mixed strategies left out of reach. The lesson from this is, again, that when you have games of imperfect recall, as in this game, the behavioral strategies and mixed strategies have different expressive power.